Isn't that something that likes a lover? Something lover.
Yep, file means lover of.
Lover of
Molecules that are positive.
Nucleo. When you think nucleo, think nucleus. Nucleus has what in it? Protons. What charge do protons have?
positive.
That's why they're called nucleophiles. They like the positively charged nucleus. Look for positive charges, nucleophiles want them. This guy, in general, has what kind of charge if you have it attached? Partial positive, right?
Yeah.
If I pull these electrons off and give them to the O, what charge does it have now? The only thing it has left is a proton. So it's positively charged. This guy goes, yep, I'll pick him up. Right? 1, 2, 3. Right? Okay. Secondary question on this particular generic equation. Which one of these is more acidic?
Hold on, let me write this down.
There are two acids on here.
The NH3.
That would be this guy's conjugate acid, right?
Mm-hmm.
Is NH3 a strong acid?
No.
It's a weak base. But in this case, it still is the conjugate acid of this base, right? There's no choice of looking at it. That's the way you have to look at it, correct?
Yeah.
Now, this is an alcohol, right? Which way will if let's say it's in, you got weak things, this won't really completely dissociate, will it? Which is the difference between this and a strong acid. This will be in equilibrium. Remember, we're retouching some of this stuff we did at the very beginning. We started talking about which way will equations go. These are all, this is a weak acid. That's not really an acid at all, but it's this guy's conjugate, so it's pretty gosh darn weak, right? So, in general,
So
which one do you think has a smaller pKa?
NH3.
You think NH3 has a smaller pKa? Definition of pKa in strong acid.
The lower to the number 1.
What kind of pKa does HCl have?
Wait, is it? Am I? Okay, wait. I gotta flip them.
There you go.
Cause I haven't done the. I'm not doing the negative log value. I'm doing just the regular
Ka.
Ka. Okay.
Yep.
So the Ka value, it would be larger.
The larger Ka value would be the stronger acid.
Yes.
You get just a quick review on Ka versus pKa. Ka, generically speaking, is just, again, it's always product over reactants, right? In general. Which in the case of an acid, generic formula being Ha plus H2O going to, depending on what the acid looks like, negative A plus hydronium. Right? It's the generic acid formula. This is the conjugate base of this acid. This is the conjugate acid of this base. Water's wonderful, it does both. Now, in general, water is a pure liquid. I don't know if you remember this from Gen Chem 2. You do not include pure liquid in the concentration equilibrium, in the equilibrium constant. Which means this simplifies to A negative, and H3O plus over, okay, because we don't include water. It's pure liquid. Its concentration is 1. So it's useless to have it in there. Divide by 1, big deal, who cares? So, now, again, we're going to get back to this because I want you, you're going to do this stuff. Okay, she's going to test you on it. So, and she specifically has asked me to bump up on acids and bases with you guys. So I'm assuming if she's asking, she's going to ask you. So, if you look at this generic equation, for every H that I pull off, which is what I'm doing, right? Every H I pull off, how many conjugate bases am I making?
One. The situation there's just one.
It's a 1-to-1 ratio. 1, 1, 1. So in reality, these two concentrations are the same, right? The concentration, I can't make one of these without making one of those in this generic equation, all right? Now I can start adjusting things by Le Chatelier's principle. What do I do if I want to make more of this acid? But it's at equilibrium. What
You
kind of things can I
add
do?
more moles of that.
Increase this,
Okay.
which pushes the equation in what direction?
That's what
What else can I do? Which is what you're going to do in lab. Remember we talked about manufacturing things?
You're gonna take the products and
Pull that off. Make this go down. Now it's going, oop, don't have enough on that side because it wants to get back to this ratio. Equilibrium is basically a ratio where the products and the reactants are being, the rates are equivalent. It wants to stay there. Anything you do to bump it, it will try to get back to. If I take this out, it goes, oop, I need more products. I made this too small now. It's not big enough. I need to make more. If I make this bigger, it goes, uh-oh, too big. I need to make more reactants. Get this back to a smaller number. That way. Dirt simple ratio. Don't complicate it. Don't make it into hard math. Dirt simple ratio. Le Chatelier's principle says get back to equilibrium. Okay? So, as you look at this, Ka values can get really unwieldy. They're like 10, if you have a really weak acid, what kind of value of Ka would you expect?
it's a weak acid.
Mm-hmm. Do you think it'd be really big or really small?
a really weak acid.
I think
You would think the
number-
Ka would be large because a weak acid
What would that
makes
mean?
a conjugate.
Using this ratio, if this is really big, what am I saying to you? Don't be bold.
More
Be
products.
bold. You're making a whole lot of product. If it's a weak acid, does it dissociate completely?
No.
So do I make a whole lot of product? Which means, again, if I have a really large Ka, it's saying, yeah, it's going to almost completely dissociate. Because it's going to make all products and kill the get rid of reactants.
So a weak acid with a large Ka.
A weak acid can't have a large Ka.
Okay.
So it's a strong acid.
A strong acid means, yes, make it all products. A weak acid means, no, we want mostly reactants. We don't dissociate much. Okay? So, again, it's just
Strong
simply
acid.
understanding the ratio.
Large.
Strong acid, large
More
Ka,
product.
more product. HCl, for example. Ka is enormous. Because it's what, pKa of -7, I think, something like that. Now, that's understanding the general idea of what Ka represents. Okay? Don't know how she could put that to you, but she could. And you know, she'd ask you in general. The reason we don't talk about Kas so much is because they get unwieldy. 3 times 10 to the -7th, or 4.52 times 10 to the 8th. People are looking at numbers, okay, order of magnitude, that's why we go pKa. It makes the numbers simple. Instead of having 3 times 10 to the -8th, you end up with, let's say, pKa of 7, or 16, or 9. Much easier number to compare, right? Little sniglet of information. Anytime generally speaking, when you see P, it means take the negative log of whatever's after it. Generally speaking. This means take the negative log of that. So, now, generic acid. We'll get back to that in a little bit. Now, again, coming back to our general equation here, we decided that this has a conjugate acid. Where's the conjugate base of this? It's the only freaking thing left. It's over there, right? Now, look at this. which one has the smaller pKa? It's the question of me asking you, what's the strongest acid you see in that equation?
There's only one acid.
Hmm?
There's only one acid.
And again, this is still technically the conjugate acid of this base. Agreed, but that should clue you in as to where's the strongest acid. I think it's here. Where's the other acid in this equation?
There's two bases.
There's on every side of an acid-base reaction, you've got an acid and a conjugate, an acid and a base, or conjugate acid, conjugate base, right? This side of the equation, which one's the acid?
Is it this one?
Is he give definition of a Bronsted-Lowry acid? I think that's what it is. What is an acid?
I haven't heard that term
Mm-hmm.
A proton or a Lewis acid, really, Lewis I don't like as
in a while.
much.
Proton donor.
An acid is a proton donor. What's a proton? For our purposes in acids,
H.
it's an H. When you say proton, think H. Why? Because it's got a positive charge. There's a proton in it. You pull the electron off of a hydrogen, it's got left to the proton. Proton donor
So is the
equal
LH.
hydrogen donor. Did this donate an H?
Yes.
So there's your acid. So this is HA, right? This is, therefore, the
Base.
base. I'll put the little negative sign, but that's trying to tell you that's the nucleophile. It's the base. I'm not trying to say it's necessarily charged. They don't have to be. Okay? So if that's true,
So then on the other side is the conjugate base and the conjugate acid.
this is the conjugate acid
Oh, conjugate.
of that base, right?
Mm-hmm.
This is the conjugate base
Of that
of
acid.
that acid. Right? Acid base, conjugate base. Now, again, if this is the acid, which one of these acids is stronger?
The NOH.
This one. What's the pKa value of an alcohol in general?
Of a what in general?
Alcohol?
Is it 16?
Mm-hmm. About 16.
Look at you. Oh, you're
Now I'm
looking
trying
at-
to
No.
pull up the pKa of NH3.
pKa?
Mm-hmm.
pKa.
My notes. I can tell you this.
We have here NH.
Notice. If you know that, I just want to show you the number, but in general, again because of the sheet, is that generally an acid, considered an acid? What's it considered?
Base.
A weak base. If that's true, do you think that pK is going to be bigger or smaller than this alcohol?
Smaller.
If it's smaller, what does that mean?
Oh, larger for pKa.
Right. In general, that means if this is a weaker acid than this is, it's going to have a bigger pKa. Smaller the pKa, the stronger the acid.
It would be inversely proportional if you said Ka.
Yes, inverse on that for Ka. That's what the negative log does. So that would mean this has a larger Ka than this. It's a smaller pK. Any luck?
I'm trying to find it, but it moves me to NH4.
I'll get to that. No luck?
NH3, is it 35?
We can figure it. Alright, we'll figure it out.
Is it 35?
Yeah, that's probably in that ballpark, something like that.
Because it said, yeah, acid NH3, pKa 35.
There it is. There you go. I mean, hell, that's almost twice as strong. And that's a really weak acid. Alcohols are not very strong. They're weak acids. But a whole lot stronger than that, because that's a base.
So then this one's 16, and then, oh wow, yeah, so when you look at the numbers, that one is...
Notice how the numbers are your first line of defense?
Yeah.
If you know the numbers, you're in much better condition, much better shape. Now remember when we were towards the beginning of the semester, we were talking about this, and you got a couple equations that asked you, remember this? How would I draw that? Knowing this information.
Knowing this
What kind of-
information, that the bigger arrow is going to go towards the reactant, the products over here. This
There
one,
you go.
sorry, yeah. And then the smaller one the other way.
Because it will try to, all this is saying, because the pK is smaller, this will dissociate more than that will. Again, definition of an acid, dissociates, loses a hydrogen. The stronger side acid, it will push it away. Okay? When you see equations and you have to decide, does it favor products or favor reactants? The side that has the lower pKa will drive the equation. Right.
So in this situation, it favors the product.
It favors the product. Okay? Now, I don't think she's going to make you calculate because that's really Gen Chem 2y. You can
She
relate
wants
them.
us concepts and stuff.
Yeah, I mean, for example, if I gave you what did I say about
pH, so it's the log of whatever's next to it, so the log of H.
in the case of acid, you're looking at, right? Now, when you look at the H+, you're looking at the concentration of whatever the acid became. In this case, what's the concentration of this over there? Okay? In the simple generic, it's hydronium directly. But this means whatever acid is creating. Okay? Now, how do you relate that? Remember, pKa is equal to negative log of Ka, right?
Yeah.
Now, if I do that, I can also relate Ka equal to the concentration of conjugate base, H3O plus, and HA, right? Meaning I can solve for H3O plus and plug it in there. Okay?
So
Also
that-
means, for example,
Wait.
Yep.
That negative A over there that you have, that's the conjugate base?
That's the products. When you dissociate an acid, the products are going to be a conjugate base and an acid over the initial concentration of the acid. Right? So, these three equations can relate each other. Given pH, I can find the concentration of that acid, right, at equilibrium. Not outside of equilibrium, but at equilibrium. Given that, I can figure out conjugate base because it has to make one conjugate base for every acid that it makes. Yeah? And typically at that point, I then know whatever I started with. I start with 1 molar HCl, or 1 molar H2SO4, or 1 molar whatever you want to give you start your initial condition. Ka. With Ka, I can get pKa. Don't think you're going to do a lot of that, I'll be honest, but you got it. Okay? I don't, like I said, you could be asked for concentration based on pH. I could have given you pOH. Remember what pOH is? Oops. idea drives away from the smaller pKa, favors the product, or depending if it's over here,
Then it's the other way around.
Favors
It
reactant.
Favors the reactants.
an easier way of testing on that is make you draw them correctly.
Make you draw what correctly?
The equilibrium arrows.
A small group today.
No kidding. Everybody's tired, I think, just burned out.
Mario's working.
Is he?
He sent me a text.
It's hilarious when you want to come before the exam. It's like you should have been here to start
It's always the same people that come, and then you see
right
the
before
people,
the exam.
you see more people right before the
That's
test.
always been true. That's true every time. They get worried when they have to study. They go, "Oh, I don't know all that."
Yeah,
It's like
yeah.
now you want to worry. You should worry about
Exactly.
it.
It's been the same people since day one, and then the same people come right before the test, and then you never see them again until the next time.
But you're not gonna get the concept if you don't come more than just that one
You gotta
day.
practice, you know.
Yeah. Yeah.
14H.
Coming here, doing the homework, studying, that helps, even though when you get your test, that's
I
a different
know,
story.
but
Okay.
This class is a whole nother
Opposite
ballgame.
side of the equation is the base. All right. What is this gonna do? We know for a fact that's a strong base, right? That's an
Mhm.
ionic bond. You're basically going to take the Na, he's going to be a plus ion. The OH is going to become a negative ion, right? So what's it going to do with this multi-purpose water over here?
It's going to combine with it.
The H is
It's going to have a whole bunch of H2O and OH. Basic equation. This is the conjugate acid of that. This is the conjugate base of that.
Can you write that underneath?
Yes, please.
That helps.
Now again, this one's a little bit weird because if you look at water, we're creating water and creating OH. So in reality, this one's going to do what? It's going to be perfect equilibrium.
Is that like the what do they call the reaction? The way you have it written there, is that the overall like condensed reaction?
You can take water out, is what you're looking at.
Well, you also the sodium ion.
Sodium's sitting around up there, yeah.
You didn't put it over on the side.
You're right. It's a spectator ion, is what it comes down
So
to.
you can delete the spectator out.
I tend to. Most people will. She will, unless she asks you not to. If I'm you guys, I wouldn't, because you're not wrong if you put it down there. It's just it's not doing anything. It's hanging out. So the whole idea here being, notice how 14 is the same. There's a relationship between the basic equation, Kb. Guess what Kb is? Concentration of products, which is the conjugate base, conjugate acid, and initial base. Right? Because again, water is pure. This one could probably come out of it too if it's pure water. So you end up with everything's going to cancel. Because that's 1. Because of this equation being so simple, everything's going to cancel and become 1. That's why that equation looks weird when you look at it this way.
That's why it's
Because
in the equilibrium.
this is going to, pure liquids, you can cancel them out. But they're also going to have the same concentrations, which is why you can cancel them out. Well, these are going to be the same concentrations too, because for every thing I pull off of here, I create 1. So everything's 1. This one happens to work out to be a perfect base equilibrium of 1. That doesn't, but obviously, it's not going to be like that. There's not going to be this simple of an equation. You're going to end up with NH3. You're going to have to reckon, if they give you a Kb value, you've got a basic solution. Okay? NH3 with H2O is going to become NH2 with H3O plus, right? So, oops. Or not H0, but it's going to become NH4 and OH, right? Like this. So, for example, what I was saying was this being weakly basic. I'll leave those out. That becomes that. Now, I didn't put in any arrowheads, did I? Why?
Because you want us to figure it out.
What is it? What is this called? Anybody know? Because she gave me this list. When I
It's a
first saw the list, I
conjugate
wasn't.
base.
It is a conjugate.
Acid.
Is that? That is a weak base. So that would mean that is the conjugate acid of this base.
Yeah,
Therefore,
yeah.
this is the acid,
So,
and that's the conjugate base. Okay?
Can you
No-
write that underneath?
If you want to, trace the H. Follow the H. We lost one here, and we gave it to this guy, right? So this is a base. This is your acid. The acid gave up an H. So following the H is very simple to find out where did it start with, where did it end up. Started out, you had 3 of them, now you've got 4 of them. Had to get it from there, right?
So I had to get it from the acid, so it ends up being
Exactly.
a conjugate acid.
You got it.
And
If
then,
you get the acid, you know where the base is. It's the other one. Wherever the H went, that's now the conjugate acid. Wherever the H got lost, that's the conjugate base. Okay? Now, if you look these up, anybody know what this is called?
What's what? What?
In general, in your terms of pKa values, she listed this. What did she call it? Anybody know?
What do you mean?
On that short list,
On our list?
pick out what that is and give me the general pKa value.
The NH4 plus.
Mm-hmm. Nitrogen is usually called, if you're in a functional group. In a functional group, what are nitrogens typically called?
Amines.
Or, depending on how many, what the type, could be an amide, could be a, what if it's at the end of a carbon chain with a couple of hydrogens coming off of it? Amine? There's a difference between an amide and an amine.
Correct.
Amine.
She has 2 kinds here. The amines, which is approximately 40, and then the other one is the pro.
You do that for an amine. There's a difference between that one and,
The other one.
is there something weird about this?
Looks pretty normal to me. I don't know.
If that's an amine, no charge, right?
right.
Oh, that one has like a plus.
What did it get?
Oh, an extra one.
An extra hydrogen, right?
So
Yeah.
it
What do we
got
call
an
hydrogens
extra
when we're talking about acids?
proton.
Proton.
See, I knew it because I was like, wait, but there's 2 of them that you're talking about, so that one would be approximately 9 then.
So this would be considered.
Protonated amine.
I wanted to do this with you guys because when I first when I was sitting on your side, I looked at this as going, okay, I don't completely understand what each of these mean. There's a couple, and most of them you do. I know what an alcohol is, but protonated amine. Yeah. She means that.
Ha, people are not going to get it. We will.
Okay. Protonated, very simple.
Yeah,
added
that
a
makes
plus,
sense.
I added a hydrogen,
Yeah.
proton. Amine, well, it had a amine. Now it's got an extra that it didn't want. Now, because you've got that, what was the pKa value? Over here? The protonated.
Approximately 9.
And where's your acid on the other side? Again.
H, wait, what did you say?
What's the acid on the reactant side?
The number?
H2O.
It's H2O, right? And what's the value, pKa value of water?
16.
Approximately 16. Which side should it favor? Yes. Yes.
Wait. I always get them. Give me time. No. Yeah.
Recall.
Reactants.
Reactants. Okay.
Wait.
Bigger line, smaller line. Right? Looking at it, it kind of also makes sense. Things that make acids stronger, charges. Water doesn't have one. I love water. It's just not that strong an acid, also not that strong a base. Useful. So
So it favors the reactants more than it favors the products?
pKa value.
It's higher.
Stronger acids over here, isn't it?
Yeah.
Stronger. What direction does the reaction go?
The
Away or
lower-
towards a stronger acid?
How it flips the pKa.
Away from the. You got it. Get used to pKa's. Get used to
So it
pKa's.
goes towards the
Yeah.
bigger one.
It goes towards the bigger pKa, if you want to think of it that way. Away from the smaller pKa.
Yeah.
Okay. This means stronger acid. It wants to give up that hydrogen more than this wants to. Which makes sense. Positively charged, not. And if you look at this, take a quick little look at these strengths. This is our first line of defense, right?
The numbers.
The numbers. You know the numbers. You got half the battle. She's going to give you acids where you don't know the numbers.
Oh, she is.
Yes. Because she's going to base it on can you piece together which
Which
one's going to be the stronger acid. It's not necessarily going to be what is the pKa value. She might give you, what do you think the approximate pKa value is? And she'll make it look somewhere in between an alcohol and, say, a protonated amine. Well, if it sits somewhere in the middle, pick a number in the middle, okay? That's what she's asking. Or favorites are the ranking problems. She'll give you a list of acids. You're going to know some of the numbers, and then you're going to have to look at the others going, what has this got going for it? Oxygen. What do you do to take a look at that? I'm going to leave oxygen, or H2O, and an H4, right? These are our two acids. I start looking at this. I need to take a look at charge, resonance, resonance, inductive effects. What else have we got in there? Hybridization. What else have we got? Hybridization, charge, resonance. Those are the big ones.
Size, electronegativity.
Size.
Right?
Size and electronegativity. That will typically be column or row issues. Okay. All right. So let's take a look at this.
It was just.
Right off the get-go.
So these are considered the trends.
When you pull an H out of these, okay, what are we saying? We can analyze it initially on the acid. If this one's fairly easy to look at a charge, this has one, this doesn't. So that would favor that this is the stronger acid. The more the charge, the stronger the acid. Same thing with a base. The more negative charge, the stronger the base. If you have,
Can I write that down?
sure, sure.
Wait, are you writing it? Okay, yeah, thank you.
Hopefully the shorthand works for you.
More positive charge,
Stronger the acid, greater the acid.
stronger.
Don't think of that as stronger than the acid. I mean, I'm running out of space, so
Yeah, that's fine.
the
So
more positive charge, the stronger the
charge,
acid.
Stronger the acid. So,
The- More negative, stronger the base. If you're comparing between charge alone, okay? You're gonna have to, the unfortunate thing is, when you get into weak acids and you're trying to compare them, they're not, there's no hard and fast rule for it. Okay? For example, NH4 plus, we said has a pKa of about 9. Carboxylic acid doesn't have a charge whatsoever, but its pKa is about 7. You think the
Said
charge,
approximately about 4.
is that what it says? Something like that, yeah.
Yeah.
But, which is weird because carboxylic, like I said, has no charge, but you're thinking, well, that has a charge, it really wants to get rid of it. Apparently not as much as carboxylic does. Okay? They're not hard and fast rule, but at least it gets you something to compare. If you have something that's NH4 plus and something with, choose it with a +2 charge, I'm banking on a +2 if I don't know. Okay? Now, looking at these in other ways, pull the H off this. What are you left with? OH negative, right? Pull this off, NH3, that looks like. Yeah.
Yes.
Now, right off the get-go, where's the formal charge on the first one?
Yeah.
It ain't on the hydrogen, is it? So, does it have a formal charge? Yeah, the conjugate base has a formal charge. What's the charge on this one? Zip, nada. Which is the more stable base?
Hold on. Stable base. Negative. Oh, never mind.
Remember, stability is opposite of reactivity.
Okay, so it's
The more stable, the less reactive. The stronger the base, the less stable. They're counterintuitive, if you ask me. They're almost like oxymorons, but the weaker the base, the less reactive. The stronger the base, the more reactive, based on stability. The weaker the base, the more stable. The stronger the base, the less stable. Pretty easy to look at these and tell which conjugate base is more stable. That means the acid is stronger. Okay? This one's the more stable base, meaning when this guy loses an H, he's fine, I'm good with that. This guy loses an H, he goes, I'm worse. I'm not happy with this, I've got a charge now.
so
I'm not
more
very.
reactive.
It'd be more reactive. This is a stronger base than that. Weak base, strong base, you can even see it. It's on the list. Right? So one of your keys, when you see this list of acids that she's going to give you and you start to rank them, take a look at the conjugate base. Look at the stability of the conjugate base. That's what resonance is all about, and inductive effects. In this guy's case, does he have any resonance? No. So, out. Does he have any inductive effects that are helping him? Not really. Hybridization. sp2,3. No. You got size. Well, alright. He's got a little bit of size and a little bit of electronegativity. I'd take that over a less electronegative atom in the same position. Right? If you had, let's choose, you got
Table.
yeah, that's what I'm looking for. Thank you. If you had, for example, kind of an electronegative atom, let's just say 2, 4, 5, 6, right? And that's a 5, so that's still got a negative charge, right? Which one of these is more stable?
Wait, let me look it out. I would say the one with the O.
In this case, what do we have to compare?
I
The
would
only thing
say
we've got left to compare here is
like electronegativity.
electronegativity. Size a little bit, but they're right next to
Because
each
they're
other.
right next to each other.
You know what I mean? They're
But
right
their
next to each other.
electronegativity numbers.
Size is typically up and down in a column anyway. Rho, like she said, electronegativity takes precedence. Okay? These are next to each other in a row. The size is pretty negligible.
Rho is electronegativity.
The more electronegative atom is happier holding onto that charge than the less electronegative atom. Okay?
So I answered
Here's-
right.
This guy is more unhappy than that guy. right? 3, 5, and 3, I think, if I remember right, something like that. So, again, take a look at the conjugate base, see what they look like. So, let's say you had, we did that, I hate to do that one again. Inductive effects. She started talking about that with carbocations. Because these can be applied to the same concept. What's the stronger acid, what's the stronger, because you have to look at the conjugate base.
Yeah.
If you have H. Best I can do. So you had which one of these is the most stable?
Is that with a bond or something?
There's a bond there. I just didn't
Okay.
write them in because it ran a room here. I thought it'd be
You
consistent.
said
Okay.
most
What's
stable.
the most stable?
I would say the one in the bottom
Why?
because it has 2 methyls.
Okay.
That's what I.
What's the
picked
next
first.
most stable?
I would pick. These are the same.
Are they?
Oh no. I see what CL. I would say. I would say this one.
Why?
Because it has a CL close to it,
What does that do?
close to the methyl. Does that mean that they share electrons better? No. Not really.
In fact, this one is based on the fact that chlorine is an electron hog. The inductive effect of the chlorine, she's right. This one is the most stable because it has another methyl group, given that it also has a Cl here too,
Yeah.
right? This one doesn't have it, but it's got the Cl. This one, the Cl is farther away, right?
Yeah.
Think of the Cl in this case, she started talking about being a proton or electron donator, withdrawing group, and electron donating group. In this case, this is electron withdrawing group, right? Think about this. If this is drawing out, this one is actually stable. That one's going to be withdrawing, so there. Comes down to one of these two being the most stable, really. Because what I created, this is electron withdrawing group. Is it stabilizing? So yeah, so take that back a little bit. I didn't look at it the right way, but take that back a little bit. If you look at this as a positive charge, this guy is trying to help by kind of lending some of its electron density to cover up this plus. Hyperconjugation is what we call it. Okay? It's trying to smother this positive charge with some electron density. This guy's trying to do the same thing. This guy's got double of it trying to do it, okay? But in the negative sense, they've all got this chlorine, right?
Correct.
Which is trying to do the opposite.
It's trying to.
It's
hog
trying
it.
to pull electron. It wants to pull electron density towards itself.
It doesn't want to share.
Right. It doesn't want to share, basically. Now, the closer you get to the carbon in question, the more effect that has. So,
Because it's hogging it from itself.
right, it's trying, this guy's far enough away going, well, I can only get so far, but it will have an effect. But the farther away it gets, the less that effect is. So, if I'm looking at this, I'm going to say, okay, inductive effects right on the carbon. That's going to outweigh the fact that this is farther away. Okay? The hyperconjugation from two methyl groups trumps the fact that this has a chlorine farther away. This effect is less than this effect. Okay? That's on a test for me. I'm going to go, okay, well, electron went farther away, so that has a stronger effect. But this has an H, that has two methyls. That two methyls, because this is over here, has a higher effect than this getting one carbon closer.
So that one would be still more stable?
This one's going to be more stable.
Okay, because it kind of balances out by having the other methyl, although it's pulling, it's still sharing because it has that other methyl.
And then this one would be the second most stable because at least it's farther away.
Away, yes.
This one would be in the middle.
So it's pulling more.
It's pulling like this guy is,
Mhm.
but this outweighs that. The positive addition of this outweighs the movement of that.
This is kind of like picking up the hydrogen bonding, you know, like pick it up, like which one has a higher boiling point or melting point. It's kind of like noticing the trend, I guess.
It is very. It's like that. What you got to find what's the most stable. How are they going to interact? Now, the idea of that was I used carbocations on purpose because you're going to practice with them a lot. You're going to get them the first. But what I was trying to illustrate was inductive effects.
Yeah.
So again, if you came back to my acid, I want to use OH, and I put in Cl there, and I have something OH and Cl here, and then I come over here, OH, oops, I write so nicely, fluorine, right? Which one of these is the most acidic?
Write it down.
We know they're all alcohols, right?
Correct.
So you can't separate them by pKa, can you?
No. But we have a difference of, is that called inductive effects? Like,
It's still an inductive effect,
right,
isn't it?
okay. And also, I guess electronegativity because one's a chlorine and one's a fluoro. So
Which
we
isn't
have,
it? That's the inductive effect that we're talking about, right?
I thought it was like the
We're
pulling.
also looking at position, aren't we?
Yeah.
This is 1, 2, 3, 1, 2, 3, 4, 1, 2, 1, 2, 1, 2, 2. So, what makes it acidic, generally speaking? The one that is most willing to give up the H. Another way of looking at it, which is like I said, you have to look at the conjugate base. Same thing as saying, what's the more stable base once you give that H up? The one that's the more stable base is going to be the one that gives up the H the easiest, therefore the most acidic. The way of asking it would be, where is the most acidic hydrogen in these three? Different ways of asking the same question. Can I take a shot, dude? You look pretty wiped out, I'll be honest with you. You look like you're kind of hanging on.
Yeah, I'm not very good at acid-based stuff, so that's one of my weak points. So I'm kind of like a deer in a headlight, trying to like figure it out as we're talking. So I think that my thought process would be, as far as giving up the H, the easiest, it would be vice versa than what we said earlier. You would think that the Cl and the one that has Cl way down here and the OH way over here, because the Cl would help try to hold that H charge. So it would make it seem like it'd be easier for it to expel.
Okay. You're right about it being the opposite of what I just gave you, because before we had a positive charge, right? The inductive
Right.
effects on this were trying to stabilize a positive charge. In this case, remember, you're pulling an H off and leaving the electrons behind. What kind of charge am I trying to balance now? Again, first step, if you're not sure, you look at it, pull the H off and see what you've got left. Just do it. I mean, flat out draw it.
Well, I mean, if you pull the H off, you're gonna have oxygen there, so you're gonna. So
Oh.
it'll be negative.
Cl, right?
Right.
These all look the same with the H off except for the substituents, right? 1, 2, 3, 4, 5, O. And then that has it here. And then I go 1, 2, 3, 4, 5, O. And that has F here. I'll draw them in, why not?
What if you do that? Like I was saying, like the F and the O, they're two electronegative
They are, but
elements.
the O can't help itself. It's got the charge there, right?
Yeah, they wouldn't want to be
They're
there.
even. These guys, comparatively speaking, are in the same boat. O-wise, their own electronegativity compares evenly, so that you can't base strength of the acid on the electronegativity of the oxygen because they're all the same.
Yeah.
There's always a comparison. The differences are
The position.
the position of the CLs.
And the strength.
Which one of these CLs is helping this O the most?
The second one.
Really?
Because you
What does
said
CL do?
it's a hogger.
And the farther away it gets from the charge, it has more or less effect.
It has less effect.
In this case, do you want it to hog the electron?
So in this case, yeah. Okay, so
You
then
want it to
why
help.
not?
You want it to pull the electrons in. Okay? So that if it's got these extra electrons, at least it's got this guy going, I'll help you. I'll be over here trying to pull them too.
Okay.
Right. This guy's farther away. So it has less help you out effect. Remember on the positive charge, it was the opposite. It's going, I'll take the electrons so you can't have any, making you more positive feeling. This one's going, you got some electronegativity? I'll help you with that. I got you.
So can I put as a note if it's positive away and then negative closer or not in every case? Okay.
I hesitate to make blanket statements like that because
Okay.
it's the, you know what I mean?
Okay, Bill.
I don't want to have something pop up and have you give
And it'd be like the exception or something.
Yeah, exactly.
Yeah. Okay, fine.
not a big blanket statement fan,
Okay,
so
fine.
like, I will never do that. It's not coming up. I will never drink again. Really? Blanket statement, poor choice. Okay, so in this case, and again, looking at it, which one would be more acidic between these two?
The first one.
The first one, because on the conjugate base, this is helping more than this guy is. Now, that said, which one is the most acidic overall?
The one with the fluorine.
Why?
Because it's more electronegative.
This guy is helping more than that guy is.
Because it's
And they're in the same position.
Because it's stronger.
It's a stronger electronegative atom. Exactly.
One.
Now,
See,
I can complicate this.
That explains it a little bit better. I'm starting to follow now.
Okay. It's very. I try to get it pretty basic, don't I? I mean, lying on the floor.
Well, earlier it wasn't as basic. Now you're getting back to basics, so I'm
So
starting to
number
follow.
one, because
Okay.
it's pulling
Um,
closer, and also because it's
now.
more electronegative. This one.
As you start to complicate these things, some of them, like the last one, when I did the carbocation, notice I had both positive and negative effects on that. All right. Things you're going to see are going to be molecules that have both. Your point is to separate what has more of than the other. For example, if you have, let's go. Right? And you have, let's do, I shouldn't have written that in because you're not going to get given that anyway. And let's do. That'd be an interesting one. If I did. question is always going to be the same. Where's the most acidic hydrogen? Where's the what's the strongest acid? Where's the most stable base? Things like that. Can I get by with just that? Let me talk that over. Yeah. Individually, I can, can't I? We'll work with it. I think the idea will be the same. Okay. What is the first thing I'm going to do? First thing I'm going to do is this. Okay. I don't know the pKa of these. I know carboxylics are, what, roughly 4, you said, or something like that? So these two are about 4, but I have no freaking idea what that is. And I can't decide between these two based on pKa because they're both 4. So, what I've got to look at is, you know, this, an alcohol in general is 16. Oops. So maybe I can. Maybe that's not going to work out the way I wanted it to. Because I got to compare it another way. Let's try. I'll have to find another atom. I like that one though. How about I do? Gotta find it. There's gonna be one. That'll work. Let's take a look at it like that. Three, four, five, six. Six. Still gonna be at 16, isn't it? I'm trying to find a way of doing this. It's gonna give me more. But still give you an uncomparable acid. Okay, I wonder if I did that. I did. That'll work. NH3. 1, 2, 3, 4. One's a 5. Right, so that would end up giving me a positive 1. The protonated amine. Gonna give you the pKa again. Damn it. Protonated amine. None of these are working for me. Okay. We'll do these really quick and easy. These are both the same thing, carboxylic acids, right? What do they got going for them when you pull the H off?
They have a methyl group.
Okay, what's helping them as a conjugate base?
Negative charge.
which one is the more, the question would basically come down to what's the more stable conjugate base. So first thing I look at, I make the conjugate base. Same thing as saying it's just more stronger acid. What are the positive things it's got going for it?
Resonance.
It has resonance, doesn't it? Both of them do. So it's, the hybrid looks like this. Right? For both of them, they have the same resonance hybrid. But the difference in them is right here, correct? In this case, these methyl groups, it's got this negative charge running around out there. Over here you've got two methyl groups that have what kind of densities? Whole bunch of electrons, or they lack electrons? Got a whole bunch of electrons, right? Now, like we said before, with the carbocation, because they've got a bunch of electrons, what did they do?
They want to
Stabilized.
stabilize.
Because they're saying, okay, you're positive, I'll smother you with my negativity. This guy's negative, isn't he? So what's their effect on that?
This one, the one on the bottom's being more smothered.
Can negative charge smother negative charge?
No,
So what's it doing?
it's repellent.
Yes, which makes it more or less stable.
If you repel
Less stable.
Less stable in this case. If it's your less stable conjugate base, meaning a stronger base, which one of these is the most stable base? More stable base. This guy is, right? Which means the hydrogen came off this easier. This will be the stronger acid. With this on with the H on here, the stronger acid is the upper carboxylic acid because it has less negative effects from these methyl groups. The methyl groups will try to repel the negative charge. Okay? You don't
Okay.
want to repel it. You want it to be happy being over there.
So with the H, it's going to be a stronger acid.
Yeah, this will be the stronger acid because it's a more stable conjugate base.
Because
Okay.
it's the most stable base.
Again, all you're really doing is comparing the relative strength of the conjugate base. If it's a very weak conjugate base, it's a stronger acid to begin with. If it's a stronger conjugate base, it's a weaker acid to begin with. Yes?
Stronger acid because
And
it's
again,
stronger conjugate.
It's a stronger acid, so it's a more stable conjugate base.
Okay.
I'm going to pull an old one out. Now I'm going to leave the equilibrium lines even at the moment. Let's take a look at this one. Because again, you're looking at very odd things. When's the last time you saw lithium acid?
No.
There you go. What I'm trying to get though is, we don't care. Notice the lithium in this case, it's an ion paired with this. Okay. What's this?
So,
What's this called?
The triple bond, it's ene, right?
It's a triple bond's an
Guanine.
ine.
Yeah, that ine.
It's an alkyne.
Alkyne. And it's got an H either end.
So it's alkyne hydrogen.
Alkyne halide.
Halides, the gases, remember.
So
How?
it's gonna be 40 to 50 pKa.
That is, you're looking at alkene and alkyl. Where's the alkyne? Because a triple bond is an ine, right?
You mean this one here?
There you go. I wanted you to see this because that's what an alkynyl hydrogen, okay? It's an alkynyl hydrogen.
So
It looks weird when you see it in writing, at least it looked weird to me. Alkynyl hydrogen, what's she mean? That's what she means.
Okay.
Triple bond with an H on it, okay? So now as you do this, again, this was your acid because it lost an H on the other side, didn't it? Trace the H. Does this have an H here?
Mm-hmm.
Does it have an H over there? The same numbers of H's?
No.
No, so this was your acid. It gave up the hydrogen. This is now therefore
Your conjugate.
conjugate base. How you doing?
Ah.
Right? If that's true, what's the relationship for these other two?
So then, this one's gonna be your base, and then the other one's gonna be your conjugate acid.
Now, this one, she gave it to you, it's on the list. What's the pK value of an alkynyl?
25.
Alright. On the other side, you actually have been given that as well in pK value. What's that one? What's it called?
For that one?
Notice, I wrote this strangely. Should I have written it like that, or could I have written it another way?
Should have written it another way.
I could have gone,
Always another way.
Right.
Yeah.
in case you see it that way.
Thank
But
you.
in case you see it that way, this is kind of being kind. It lets you see where the H went easier. This one, you kind of go, oh, there it is. You have to pick it out. Okay? But it's the same equation. So now, where's the, if this is the conjugate acid, what's the pK value of that conjugate acid? And what's it called? Nobody?
Is that one? Hold on, let me just go like this.
Is the top row the product?
Reactant?
I'm sorry, the reactants.
We haven't put the arrows in right now.
Okay.
Because they're in equilibrium. It's not a strong acid, it's not driving the product. It's a weak acid. So this is called, so I'm trying to get you to go through everything on here so you've seen it. You know what it is. That's what my purpose right now is. And of course, evaluating acids and knowing the pKa's and drill some of that. Is this thing an alkene, an alkane, or an alkyne?
One bond.
It's an alkane. An ine is a triple bond. Does this have a triple bond?
That would have on one bond.
It has a single bond. It's an ane, which means these are what do we call these groups individually? They're all anes. They're alkyls. Notice we go methyl, ethyl. When they're substituents, those are called alkyls. Okay? Methyl, ethyl, probyl. When they're attached,
One bond will always be
ill. They're alkyls. Okay? So if this is an alkyl, what's the pKa?
40 to 50.
You got it. Which direction is this thing going?
Towards the product.
Yep.
Yes.
Alright. So far, so now you've seen a nitrile, an alkyl, or not a nitrile, a protonate amine, an alkyne, alkyl hydrogens. Alkynyl hydrogens are the same thing, you just got a double bond in there somewhere. CH2, CH2. Alcohols. Let's see. There's something we don't have. What on that list have I shown you here? Oh, the strong acids are fairly easy. Okay. We did this. Let's just do something interesting with that. Alkyls, protonated amines, regular amines, alkynyl. Okay. Right. Yeah, I flipped it over. I won't do that to you. All right. Which one is a stronger acid?
On top,
Why?
double bonds.
Good, good. What is it called?
Alkyl.
They're both alkenes, aren't they?
Oh, yeah.
What's the difference, and why would that be a stronger acid? What can you do with
Because
this?
of resonance.
Bingo. What would they call on the list then?
That what? What are
What's
they
it called on
the
this list then?
I can't say that. Hydrogens with resonance.
Alkyl hydrogen with resonance
Alkyl.
stabilized anions. The words sound funny.
Yeah.
That's what it is.
It's a mouthful.
All it's saying is, when they say anion, that's the negatively charged conjugate base of the acid. The anion is simply the negatively charged conjugate base of the acid. It's what you got left over, okay? In this case, let's say I pull an H off of the end here, right? So now I've got something that looks like this. 1, 2, 3, 4, 5. Ding. Yeah. Let's do the exact same thing with this. 1, 2, 3, 4, 5. Ding. Oh, I take that back. Negative. Yeah? I pull a hydrogen and leave the electrons behind. That's the anion of this. That is the anion of that. Anion, conjugate base. Can I do anything with this? What's hybridization here? I'll do it.
No, you're going really fast.
Yes.
Am I?
And I have to write
When you
stuff
said,
down.
can you repeat the last thing, the conjugate?
This is the conjugate base of this acid.
Okay.
Not that it's much of an acid, but for its own sake.
And
That's the conjugate base
anion,
of,
right?
that's the anion. The same thing in this case, saying the conjugate base, okay?
What about the other example? Which one is the?
This is the anion of that, or the conjugate base of that acid.
Okay, so now you can ask me about hybridization. That's going to be sp2, sp2, and then sp3. Let me catch up.
So again, I ask you, anything I can do with that? It's stuck over here, ain't it?
Yeah.
So that was this one.
sp2, sp2, sp2,
Then you have
Whee!
bases.
Off to the races. Right?
Yeah.
So it's got the resonance structure that goes like this. Right? So that's why, again, what promotes stability? Resonance. The conjugate base has resonance, meaning the conjugate base is more stable. More stability, less reactive. Okay?
More stable compared to the acid, or more stable compared to the other base that we were looking
More
at?
stable compared to the other conjugate base.
Okay.
Remember, if you're comparing two acids and trying to figure out which one's more acidic, the one that has the more stable conjugate base is the stronger acid. It feels a little backwards in the wording, but that's how it works. Okay. Now,
So we would have to know what the base is, draw the base.
yeah, like I said, first thing I do if I don't know by pKa value alone, I mean, know the pKa values. Your first line of defense in this is dirt simple. Just know them. If I don't know the pKa value, then the first thing I do is pull the H off and see what I'm left with. And I start looking for resonance. I start looking for what else has it got that's going to help inductive effects. If it's got an electronegative atom helping to pull that negative charge in, has it got anything against it? Going against it, trying to push the electrons off, making it more reactive, and then I compare them. You have in her general terms, these are all strong acids. We know that, right? HF is the only one that's really not a strong acid, weak acid. But the other three are. What's the rule we apply to decide on which one's the strongest?
The biggest.
Why?
More mass.
More area. It's got more spherical area in its outer shell to hold more electrons. In this case, Cl is the smallest, right? I believe iodic is the biggest, right? Oh no, bromic.
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 I can tell you.
Which is bigger, I or Br?
BR. No, wait, I.
I
Yeah, 126.
here, 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 right, based on size. You'll get a couple of those mixed in with a couple of. Why then is that stronger? And it is, I can tell you right now, the pK of that is like negative 18. Okay? It's enormously acidic. Way stronger than any of these.
That's just, is that part of the strong acids?
Oh yeah.
So we just, because we memorized.
See what I'm saying? But your list says they're all less than 1. True. They're all less than 1. What are you going to do? Uh-oh. Well, now I got psi. I can get these into order. Where do I put this guy? I just told you because I know the number. But what if I don't? Do you know the difference in the numbers between this guy and these?
No, sir.
So what's if I don't know, what's the first thing I do?
Well, you can actually do it by weight, by size of the molecule.
No, because that's individual down a column, remember? The size rule applies down the same down the column. This is a conglomerate.
It still kind of work though. Because sulfur, oxygen, hydrogen would be more
4
than the
oxygens.
hydrogen.
But where's the hydrogen on that?
Front.
Remember when we built it?
They're on the oxygen.
On the oxygens.
What does that mean? I feel like we draw that in every exam.
Some form.
And I
You
always
draw
get it-
something.
And I always get it wrong. It's just, I have like minus. I think good.
But the total weight of the molecule is bigger.
Yeah, it doesn't work like that though. I understand what you're trying to say, but where the electron, if the electrons are here, it's this atom that's trying to hold them. You'd have to be comparing the O to the Cl, the Br, the I. It's not this guy trying to hold them. He might be trying to pull them in, but he's not holding them.
Okay.
Size-wise, it's the guy that's holding them. Okay. That kind of brought up a good point, really, I think. It worked out for us. What do I do with this? What can I do with this?
Resonance.
Because the first thing I'm going to do is pull the H off. Look at the conjugate base. Well, S doesn't have to do anything. It doesn't have to obey the octet rule, does it? Which is why I drew it in with all those little lines. But because of that, it also means I can take this and go anywhere I want on S, except where? SP23. Ain't going over there, am I? Not going there. You see it?
Do I give up always
Stop.
one H?
Okay.
Stop me. Like I said, if I don't know, the first thing I do is pull off an H and look at what's left.
Do I always pull off one H?
Always pull off one H, because the second one, this is diprotic, and it will, this will dissociate in water. Really difficult to get it to do so. It's going to have a Ka value, which is really, really, what?
Large. You said K. You
I
didn't
said
say
Ka, I did not say pKa.
K.
I said
if
If it's
strong,
really, really difficult to get that second hydrogen off, its Ka value will be,
lower because it's.
it doesn't want to become a product, does it? Doesn't want to make a product.
Wait, but what is that? What does that
But
mean
how
again?
can a strong
In this-
acid be? Wait. We gotta back up here. How can a strong acid be a weak acid?
It
If
can.
it's a strong acid, then it's a strong acid. It's a strong acid.
No.
Then it
This
means
is
it's
a
gonna
strong acid.
Then it's gonna mean it's gonna completely
This
dissociate
is a strong
in
acid.
water, right?
This is a strong acid. That first H is a strong acid. Does this have that first H? This is now missing that first H. It's now HSO4 negative, isn't it?
All right.
What's the conjugate base of that? This is the Lewis structure for it, but if I drew it out, take an H off, take the 2 off, and add a negative. HSO4 negative is the conjugate base. But it still has a hydrogen, doesn't it? What if I asked you the acidity of HSO4 negative? There's an equilibrium constant for it. That H will come off, but it's really hard to get it to do that because its Ka value is really small, which means its pK value is really big. Inverse relationship, get that down, right?
Can you go back to that concept? What's the relationship between Ka value and
I think the stuff from the
I
beginning.
know pKa
These guys have seen it, so I'm going to ask one of them to do it for me.
Yeah.
Who wants
My
it?
notes.
I know pKa is the inverse of Ka. If you have a large Ka, you have a
Small pK.
pKa.
Because, again, I'm going to make what do you guys got to hop up here? I know
I've been
you've
talking
seen it.
all
Now you
morning.
get to teach it. You can teach it. You got it.
I've been talking all
Well, I know I don't have it, so I'm not teaching.
When
Right,
you
exactly.
Smaller
remove
pK, larger acid, right?
Can you write this, do the equation for it, if you wouldn't mind?
This is the equation we're talking about.
the generic, the
Mhm.
general one.
That's the generic one, and then
Okay.
I want you to relate pK to Ka. That's the big
and in
equilibrium
that
constant
example,
for
what
it.
just happened when you remove the H where we combine
We're going
it
to come
with
back
the-
to it,
Okay.
I promise. Because here's why, in my opinion, HSO4, H2SO4 is a stronger acid than the rest of them. It outweighs the size effects. But it also brings back to the forefront all those things you're trying to balance.
I'm running
You
out
know,
of
you're
space,
you're
so I'll just
analyzing
write
all
under
this
here.
different stuff, and you got to weigh it out and see which one you think is a stronger effect. Wow, she writes a lot better than me.
I know she has nice handwriting.
Oh,
Yeah.
thank you.
That's why I make her write map.
That's true.
It's funny.
Yep, that's the generic K
And
constant.
the log, you want me to write that down?
pKa by
Yeah.
remove P's. See? pKa is the negative log of Ka. All it does is reverse the bigger number being more stronger versus the smaller number being stronger. Because Ka's get really out of hand as numbers, they become times 10 to the negative x or times 10 to the positive x. They're just kind of unwieldy to compare and look at. pKa's, though, instantly turns into numbers like 4.2 or 15.3. I can compare 4 to 15 all day long, easy to look at. It's all it does. But it also means, like you said, the larger the Ka, the stronger the acid. The smaller the pKa, the stronger the acid. Right? Now we went through and related pH to things, but
I have a strong base on that.
You want me to write that
That was
down?
chemistry.
now you good. So, okay. That just looks too pretty. Now, this guy, again, he doesn't have to obey the octet rule, so there's a lot of things I can do with it. I just can't go there. That's blocked off. Game over. But I can do this with resonance structures all over. Take that and go, whee! Right? Yeah. And then I can go I'll just push it back down and push these ones up. Yeah? So I've got at least 3 resonance structures right off the get-go. And pretty electronegative atoms in O in and of itself. Right? It's not like O is a weak electronegative atom. Right? In fact, if you start looking at electronegativity of these compared to Br and I, again being an inductive effect, that also kind of says, okay, it's not only has resonance, it also has electronegativity saying, okay, I'm pretty good with electrons. I kind of like those. These guys like them, but relative to oxygen, what's their numbers? See what I'm saying? So in this case, those two possibilities, the inductive electronegativity and the resonance outweighs the size factor of those atoms. Okay? So you got to look at if you have more than one thing working for you or against you, you have to track them all. Break them down. When you first saw this, I would imagine you weren't thinking, oh, and it's got electronegativity. You saw the resonance instantly. Or could have gotten to the resonance, fairly straightforward. But then that secondary argument on the fact that, okay, well, this is an electronegative atom. It's not horrible with holding on to electrons. So are these, but it's oxygen. This has 2 effects going on, that has 1.
Correct. So
Okay.
that's why that one would be number 1.
You got it.
And then we can just go.
Then you're down to size on the rest of them. Okay?
Yeah, 2, 3, and then 4.
Mm-hmm.
Right.
Yep.
And what was the question that you asked? Why?
Why is
more
H2SO4 a stronger acid
Right,
than
stronger
the HCl, HBr, and HI? Right?
And-
Which we all know are strong acids. Everything in here is less than 1. That's what you've been given as a general rule on your little chart, right? If you had to order these and they're all less than 1, you can do these based on the size rule because they're in the same column.
Correct.
This guy's nowhere near that. You have to find another way.
Yeah.
Okay. Now I don't know if she also gave you a sheet with some specific pKa's, didn't she? I did. I gave you one at the beginning of the semester with specific pKa's.
I think so.
Do you guys have that still?
No, my phone.
So much stuff.
And then electronegativity worksheet.
I just wanted to see the what you do and don't have for pKa values.
I remember you gave us a Vesper worksheet thing.
Yeah.
Common acid and bases
Really
one.
early in the early in the semester because we were getting ready for that first test, and she was talking about including acids on there.
pKa is an important Bronson acids. Is this one it?
Yep, that's the one.
Zoom it in. Which
Okay,
way?
this is probably bigger than, might be bigger than the one she gave you. It's certainly a bit of overkill.
Yeah, I think so.
But
It
take a
looks
look
like
at
a
'em.
lot.
You know what I mean? Take a good look at them at least once. First line of defense is that pKa value. Right?
pKa.
After that, you've got to go to this stuff:
That
resonance,
this was
size, conductive
August
effect.
29th. Do you have it by date or something?
So the more things it has makes it more stable or less stable.
You got to have each one of them. In this case, size. The bigger the size, the more stable, right? Because again, what you're looking at is
Yeah,
conjugate base.
I was studying.
I mean, we can always think about the bigger with the HSO4 case. The bigger it is, the more more acid it is. No.
Well, again, in this case, this is not as big as this or that or even Cl.
It is if we think about the O times 4.
But it's not. That's what he was. That was the point Chris was trying to make. Was
Yeah.
it's what's it connected to. This, in this case, the reason this works out based on size is its conjugate base is simply that halide, and it's saying, I've got this much room for those 2 electrons that I now have to hold. That I have this much room. But on the H2SO4, both of them came off of oxygens, didn't they? So where are those electrons going? Are they going anywhere near the S when they come off? What's the atom trying to hold it? O is. O is trying to hold it. Does this guy ever hold it? And is this an overall atom that's holding it? No. They're going right there. O. See what I'm saying? Size-wise, that doesn't work. You can't compare SO and these. You have to compare O and these. Oops. That's ugly, but I guess we can do it. Can anybody tell me what that's going to turn into?
NH3 plus.
An H3 with no charge, right?
Yeah.
Because this pKa is larger than that, or smaller than that pKa, right? Because between the 2 of them, that's a stronger acid than the alcohol. Right? So the H is coming off of here. Notice I didn't give you water. Bummer.
Water.
But I don't care.
It just falls out anyway.
Yeah, water falls out and it's easy. Hey, hydronium ion. But because I know this is a stronger acid, that means the H is coming off. It means it's going over here somewhere. Where do you think it's going?
To the O.
Why?
Because it's more electronegative and that's
It's
where
got
it's
it.
pulling it.
That's all it's got, isn't it? There's no polarity here. The only place this can go, right there. Now what happened? Is O happy? O was happy. No, O's not very happy. O's got 1, 2, 3, 4, 5. Right? So it used to have a 0. Now it has a. Look familiar? It's kind of odd. H3O plus, hydronium ion. Now you got a charged water. Ew. Now, the point I'm trying to make on that is just because this isn't water or something simple, you now have to decide which one's the acid that the hydrogen's coming off of. Okay? Well, how do you do that? Well, I look at a pKa value, I know that's smaller than that. But you could also look at, okay, what's the conjugate base of this? Right? If I look at this, which one's more stable? This guy, right? Which means this guy's H would be apt to come off, making this the acid. Okay? And this, the base. What I'm getting at here, what did I get to? This is easy, right? But if I give you something that isn't so pretty, and you're not sure, you gotta look at the, well, that's a pretty stable little ion all by itself. It doesn't want to lose an H, which is pretty, what's the pKa of an alcohol? Roughly 16.
Why is that one stronger again?
Why is this one stronger?
No charge.
This is a more stable base than its conjugate acid would be. Weird thing though is we base our pKa on that being the acidic hydrogen, isn't it? But in this case, it's not. It's an OH, if you want to think of it that way. It's going to attract the hydrogen that this desperately wants rid of, or wants rid of more than this guy wants rid of that. Yeah? So,
Should we get used to seeing the reactions in skeletal mixed with?
yes, yes. Because there's no skeletal to this, is there? In our notation. You could draw a Lewis, but she's not going to do that. There's no skeletal in this. We always write, if I had an N out here, we'd say NH2. NH3, whatever we had on there. NH2. So, and a kind of, is there a skeletal for this? There is for this. This, you might even see that as, if you don't have to do it yourself, you know what I mean? Various ways of looking at it. Oops. That didn't work out, did it?
No.
Okay. So, let's see if we can find something in this little gem that would be ugly to look at. Because that's the other thing I've noticed as of late. She's looking in the book a little more. I'm not used to it. It's not something she was doing a lot of prior to. But she is looking in the book more these days. And she said, ooh, that's a nice problem. Ooh, that's a nice problem. Ooh, that's cute. It would behoove you to do the brownie points if that's true. Just saying.
She hasn't posted them yet.
I'm just saying when she does, if she's looking at the book.
Yeah, because she used them for the quiz. She used some of the brownie point things for the quiz.
Right. And I wouldn't be shocked if she pulls some out. If there's a test coming up, boom, there's one. Because she thinks they're
I want to
nice.
see those brownie points. That's awesome. That email. She put a lot of stuff in.
Anybody have their book with them? I forgot mine on the counter. I know exactly where it is. I know what I was looking at. But there it is.
She posted a lot of things in Canvas. I don't know if you guys have checked. She posted 3 classes worth of PowerPoints, and she did put the lab.
For this week.
Yeah, the 3 lab in the lab, and then the grade.
If I had that. Interesting. If you have, let's see if I can make hydrogens with any of these. Without the question, it's kind of hard to ask them, isn't it? Nobody? It's just resonance structures. We might have to work on some of these on Monday then.
Is that the answer book?
Yeah, but it doesn't give you the problem,
Yeah.
so I can't present it the way the book is without having the book with me. Like I said, it's on the island in the kitchen, sitting right there. I can see it. It's just not there. Because the answer, what are the structures of glutamic acid and cysteine? They're fully protonated. what's the acidic pH? What are the pK values of each? What is the ratio between pH and pK values? That's easy. Which one we remove first, and at what pH? All right. Fully protonated form. Okay. That being the case, like I said, I'll work some over and find the problems at home. What?
On Monday?
Monday sounds good.
Monday, Sunday.
Yeah,
Chris-
I know.
Chris looking for a nap, doesn't he?
I'm like tired.
Eat some
Okay.
caffeine or something.
What do you guys want to do as far as stuff we've already looked at? As far as things that you think you're struggling with at this point? Still or not seeing?
You know, at this point, I don't even know because, like, I had the whole big old booklet of, like, the study guide and stuff, but to see, like, the mistakes that I did on the exam, you know, like, I thought I had it pretty down packed.
I don't know really what mistakes we've made on the exam yet. 'Cause
Exactly.
we really haven't had a
To be
chance
like,
to go all the way
which
over
one?
it.
I'd be like, oh shit, I thought I knew this, or I thought I knew that.
I
so.
do know, like, my mind placed the cyclo on the wrong thing.
The question that was worth 18 points because it was 2 cards. I did that one wrong where you're supposed to show her represent how the molecule, what is it? How the oxygen.
Did you have it basic? Was that the one
Sodium.
where she dissolved it? That she had a sodium, and how it worked? How it was basically in a polar protic solvent.
Yeah.
Water, I think is what she gave you.
But it wasn't.
When I draw
You
my
had to
like
draw
my
it.
picture, I draw
Backwards.
backwards, but because I thought when you have like a complex bottom, like the whole figure, and that's what happens, that you cannot get through the thing because you have a complex
Oh,
bottom.
you're saying why does the polar protic
only dissolve
dissolve one or the other one
cations and
can't?
not anions.
The cation,
I had
cation.
Oh, I
NaCl.
didn't know that one.
I had that one wrong.
Did you?
Yeah, that's the one that me, Alan, and Brandon, we like wrote it down and redrew it.
I
When we did it,
Like,
we did it in practice. Remember when we dropped it? It's just you can't get to it.
Yeah, pretty
Yeah,
much.
that's what I did. When I draw it, I put it where you can get to it. So I put all those weird things, trying to hit the
Did she
Cation.
give you sodium chloride? Just plain up salt.
I don't think
NaCl.
so, yeah.
So what I did, I drew it all with the bottom, trying to hit the Na. And she said backwards.
Okay. Just real quick.
Oh, the lambda max is
This
the one with the
came
most
down to the one with the
consecutive.
most
Yeah.
conjugating double bonds. Remember, she said the more double bonds you have, the more light you're going to absorb. Most.
Yes.
Wait.
They had to be consecutive.
Yeah.
Yes.
Remember, I said basically when you have
The
when you get to
most
6
double-
conjugated bonds, you now start taking up visible light.
Right,
Meaning
which
it's,
means a higher wavelength,
yeah.
higher frequency. Because
Yeah.
when you measure light, it's
I didn't
in
know what it
nanometers or it's megahertz.
Depends on what you're.
Yeah.
Well, yeah.
So
that's
the way I
wavelength
look at it
versus
is
6.
400 to 800 megahertz that you can see the light in. So on the graph that she gave us to study, the shorter the wavelength,
Well, hertz
Well,
is cycles.
the shorter-
Wavelengths is different.
the shorter the frequency,
Because remember, lambda is wavelength. And remember?
right? But they had it to where on the thing that she gave us to study, it was different. There was a graph showing like one at like point. I'm trying to remember, it's like 1.5 or something like that. It absorbed like 1.96, and they had another one at like 2.56.
In wavelength or in frequency?
They had it in frequency, but it basically gave proportional to if it was a faster frequency, then of course it's going to be a shorter wavelength.
Typically,
So the longer the wavelength, the higher the absorption rate should be.
which still comes back to the more frequency you're absorbing, the more wavelengths you're absorbing. See what I'm saying? If you're capable of a range of frequencies that are from here to here, you're capable of a range of wavelengths from here to here. If that makes sense. Think of it as wavelength the magnitude of the wave versus the frequency of the wave, or you might be looking at it the other way around. How many you can get per second, or whatever.
What the cycle rate is.
How big they are. Now, if you're covering more of those frequencies, you're covering more of those wavelengths. Yeah? Meaning bigger ones, shorter ones, everywhere in between, right? So which means, based on lambda, you could have a lambda that's this big if you've got enough double bonds. Versus if you can only cover this much frequency, you can only get enough lambdas to do this much. Right? Because she was talking about absorbing
We-
IR, right?
The way the whole graph was written, it was written backwards. Because the way the graph was that she gave us the study was showing it to where it was going to be less double bonds had more absorption rate than the higher double bonds.
Absorption rate. I'll have to look at that. See what that graph looks like.
And I don't have all my stuff here. I would show it to you, but
That was another thing.
I'll look at it.
Interesting.
I'll try and find it on Monday, and I'll
Cool.
bring it in so you can see it. And
Cool.
So we can maybe me and Mario interpret it wrong, but
We'll piece it together one way or another. I mean, we'll take a look.
I'm sure we'll see it again. So it's good to know
I don't know.
how
Yeah,
we pieced it wrong.
The only thing that is weird about that is, again, okay. You know what I mean? I'm looking at it from a point of view of where we're going. Then I don't want to
Yeah, it's
diminish background. Obviously, understanding what's happening, I'm a big
I
fan
think
of.
it was mainly to help us out in the lab, is why that was.
Yeah,
started
I think
there.
so too. And because if I look at where we're going, we're all going to reactions. That's where this is all headed. And most reactions come down to to recognize stability of conjugates, stability of the molecule you're making, and you're looking at, is it a protic or aprotic solvent? Because that affects the nucleophilicity, which is again about stability. The electrophilicity, which is again about stability. How badly does this thing want to get a hold of a positive? How badly does this thing want to get a hold of a negative? That doesn't help me. See what I'm saying?
Right.
I don't care what wavelengths it has. Which is why a couple of these I'm like, wow, okay. And the bond thing. Okay.
I was luckily I remember
I got
that
that
from
one
way
wrong.
back in the day that
One
if
for
it's
free, I
shaded
read, the
and
other two I didn't
not
know.
shaded, then it's anti-bonding.
Right.
You got
It's,
that right.
if they're opposite
I
each
don't
other,
even
it's
know.
anti-bonding.
That's
If
the
they're
thing. I got my
equal
test
to each
back.
other,
Sometimes the
not,
questions,
with
I don't
each
know
other,
what
it's
you wanted
bonding.
to see. Like, I don't know what the
Um,
question was. I don't know if that happened to someone else, but
That was like
there, I didn't know what she was asking for, to be honest. I kind of put like a pie on two responses and the other symbol on another one because I
Okay.
didn't know what was.
If you look back in your notes, it is actually in there. It's because this means they're in the parts that are next to each other are in phase with each
so
other.
they can bond.
Okay, so they can bond, which in this case, is sigma, right? Because they can only bond on one side because of the orientation, right? These are the only sections that are going to overlap, not both. This one and this one are out of phase,
Anti-bonding.
can't bond. And if they could, how many
Sigma.
parts would overlap? But since they can't, right?
They
then
could bond.
Could
They
not.
can-
this one cannot because they're out of phase. Notice the part that is oriented next to each other are completely out of phase with one another.
Yeah, the shaded and non-shaded, so they can't.
Were they were anti? Okay. When these overlap, there's two sections that can possibly overlap. Remember, we drew that weird looking bond when they are together and you put the little electrons in it? Eh. Well, this could overlap in two places, which means it's,
High
but they're out of phase.
anti-bonding. And then she had another one I think on there was pi bonding.
Did she? Might
There
have
was
been.
4.
If it could overlap in two places and they're in phase, then
Yeah.
yeah, we're golden. But, which again to me, okay, that's okay. I don't think a whole lot about that stuff when I'm looking at how things are reacting.
That
That's
was
the
a
first thing, like,
2 question again.
So you think that's good? Because we just kind of started this new section. So you think this is good for what we started, right?
Acid wise,
Mm-hmm.
yeah, you're like I said, you got to practice. Get in the book. That'd be a good way of doing it. Because
Yeah,
look
she
for
said
things
read
that you don't
chapters.
Yeah,
just
she
know.
did mention
You know what I mean?
that.
Yeah.
I think that's why I'm kind of lost because I need to go back and read the acid-based chapter out of my
Well,
organic book.
Strangely enough, we're doing acids, bases, and Chem 2 as well. So I'm getting a lot of equilibrium constant and log constant, pOH.
Are you taking
pH.
chemistry 2 now?
I'm teaching. Yeah, I'm doing this for Gen Chem 2.
Oh, okay.
So there's deciphering between what's relevant to organic versus what's relevant to Gen Chem 2. And the equation-wise, no one understands what the equilibrium constant is and why that becomes pKa. That applies to you guys all day long. Figuring the calculations to get from
That'd be Gen Chem
ice
2.
tables and things like that, I think that's too Gen Chem 2y to be useful to you guys.
Yeah.
But I'm not giving you the exam.
Of course.
When
I don't remember there was anything really on the test stuff that
Yeah, I
until
would,
we actually go over it. Like I
and
don't
get
think we
it back.
really we won't have like any really good questions.
and if it was like actually a mistake or like a stupid mistake, 'cause
we
we
should
were
give you the
rushing.
solves.
Yeah, most of the stuff like usually when we look at it, we're like, why the hell did we do that? Like we already know like we shouldn't have done that. At least the ones I look at anyway are like that.
Which one's polar protic? As a solvent, which one's polar protic?
H2O.
H2O. What's that make the other one?
A
Hey,
proton.
But it doesn't have a,
Hydrogen.
which is a proton,
Mhm.
polar aprotic.
Which means it likes to do covalent.
You got the thing. Here we go. If you have this little Na, after you break it up in water, let's say it's in water this time. The O is partially negative, so it's going to
Attract the
Bind with the sodium.
all the way around it, right?
Yep.
And I mean, how you represent it, how small you can write comes down into it, but I can't write that small. So
Me neither.
pretty easy, right?
Mhm.
On the CL, it just does the opposite. The H's line up, right?
But that's not the example she gave us.
But see, doesn't that H and the O also kind of attract a
They-
little bit? So
they're
it
in
kind of
water.
like smushes down just a little.
You've got a lot of hydrogen bonding between the water itself.
Yeah.
But the point of it was to show what it does with the chlorine, not to necessarily to show what it does with its other water.
I drew it with the chlorine
You could
bonding and then put the H a little bit bonding too.
You can. I mean, because it is doing that. But the point of the problem was to show what it does with the chlorine.
But it had a weird shape.
Well,
Oh yeah.
It was like a house. Like the O, I don't know if that was there were two questions. One of them had like a house shape. O
You may
and
not
a
have-
house shape.
it depends on what you had with the nitrogen. If she gave you a sodium,
You mean it's another question you're talking about?
Maybe, yeah, because there were two questions in that. And the one I had, it was like an O, but then it had a house coming out of
a
it.
cyclic,
Yes.
that's still basically what she's trying to tell you there is you've still got a polar aprotic solvent. If you're saying that instead of it being looking like this, what if I gave you a solvent that looks like this?
Correct. It was looking like that.
Still polar, but aprotic. Where's the partial negative?
Right there.
A product meaning that it can only go with cations.
It will. What it's trying to say to you is,
Cations.
where's the partial positive on this? On these carbons, right?
Okay.
Right? Now, if you've
Oh,
got
I
this, I can rotate this house all the way around the nitrogen easy.
The way I drew it.
House,
was-
house, house, house. Which, all up, you want
This is how I drew it, and she said in hers because I started doing this. Oh. Started drawing it like this.
yes, because you've got the partial negative going the wrong direction.
But at the same time, isn't it part of the definition that this is making it hard to get through the?
You got
Or
the
am I
wrong atom.
mixing? Am I mixing?
It is really difficult for it to get to that guy. but it's not hard to get to that guy because the partial negative is exposed.
So I should have.
You should have-
done that.
you got it.
Like,
It's easy to get to that guy, can't get to that guy. You can get to the
Because
cation.
I'm gonna be here,
You got it, and you got
and this is
the positive going away over.
Oh.
The negative's trying to get away, and the partial positives are over here. So you're trying to turn it towards the.
Yeah.
They're repelling. You know what I mean?
I probably got the definition on the bottom right, explanation, but the drawing was horrible.
Yeah, like I said, it's just a matter. Like I said, it can't. This when you actually have it as a partial negative, partial positive.
So I should have
You
done
can't
that.
get to that to get to that. I'm trying to do this, right? Alright.
So nice to know it now, after the exam.
I can't get
I got it
there.
wrong.
Cannot get to you. Too hindered by things in my way. In the immortal words of James Seeger. Cannot get there.
Bill, I should have known this before the exam. What
You
happened to
did.
me?
We did that. You don't remember? Were you here? Maybe we're like, because we did one
I got my
here.
concepts confused.
We tried to straight, because we did it. Why can't it get there?
Yeah.
Because I think you
I
guys.
remember you said can't get there, and we're like, we're gonna write can't get there, and you were like, no,
I even remember that. I even remember that
Might
joke.
not be the most eloquent way of putting it, but that's
I
what
even
it comes
remember that
down to.
joke, but I missed putting the partial, positive, and negative. I missed the whole point of making the negative in the
Mhm.
positive.
If you had put in the partial charges, you would have seen it.
Yes.
Which is why I put
absolutely.
them in this time.
Yes.
And
Well,
sorry.
I hope she has the same question again.
Yeah. There's been a lot of those questions.
And this one can replace the first one, right?
I wonder.
Your best one can replace the first one
As
out of all the tests.
I wonder if so. What happens then? She gives us double that point, or it's just a one grade? When we replace it, are we gonna get two of the same grade?
Yes. At least that's how it was done
But
for
that's
us.
gonna give it more weight. Okay, we get a.
It would depend on. I mean, that first test is the only one she's willing to kind of replace out. She's not going to take your third test and replace your second test. She's not going to take your fourth test and replace your third test. She'll take your fourth and replace your first. Your third and replace your first.
Okay.
Second and replace your first.
So
Whichever
like you
one's
said,
the
the
highest.
highest
Because
one.
she's getting rid of the lowest weighted one.
Mm-hmm.
She's allowing you to redo the low weight one. 5%.
Okay.
That was 5%.
Yeah, the 5%.
No.
I see. So we're gonna have two of the same grade.
Right.
At least for now, unless we move on, we get higher, and then we can replace it.
Which is still kind of promising that there's still a possible A hanging out there in Lavoville.
I
gotta
know.
be
We
had.
all have
It's got to
that,
be had,
that
right?
hope. We all have the hope. And Bill, you're gonna get us there.
If I could just, I really want you guys to do it. I really do. I promise. I swear to God. Like, come on, you can do it. Because we're looking at it. I stayed for a little while. You guys were partially because I wanted to see if somebody stood up, but nobody did.
I used my
Bomb.
markers, so I was
What?
like this.
Come on, do a Fisher.
We didn't have time.
That's
Bill,
why I
have we
told
done
her.
that
I
within
was
10
like-
minutes? I mean, how are we supposed
Newman.
to dance and then do the exam? It was 5 pages. I mean, when I saw that, I freaked out. When I
I'm
saw how
telling
many
you,
pages
I'm
it
telling
was.
you. When she was like a half an hour, I said, "What the hell?
And you
What
still had like 2
time is
pages
it?"
left?
I just started.
I know.
Like,
And we were already tied from the brownie points. So dancing would have taken 10 minutes that we didn't have. No. I was like,
Gotta go too fast. Gotta go too fast.
it's not only the amount, it's not only the difficulty, is the stress that
no,
everything.
the problem
Testitis.
takes
Testitis will get you.
time. Those problems.
Do you have any Fisher projection issues?
You
Those
know,
come out pretty
I
straightforward.
I
Enantiomers,
think so.
diastereomers, because we pounded the daylights out of those.
know that's why I was like, I don't know what I think I did it right.
Then
I
I
thought I had
diastereomers,
100.
you can still get confused on those if you're not
Yeah.
careful. But as long as you do the, as
Those
long as you
R
do
and
the
S.
S and the R, then
You should be
won't-
fine.
You won't
Yeah,
be
Should
I
be
don't
fine.
know what I got wrong.
It's when you don't have all the information to do the S and the R sometimes.
Back to NaCl with the, was that polar or polar?
Polar aprotic or polar protic?
Yeah.
Which one do you want to see?
I was doing it with H2O, right? Yeah.
H2O is polar protic. That's done.
Yeah.
Is there anything all over?
Water's polar, so you gotta remember.
Oh, did you ever end up posting that other one? Because I don't know where you're putting these at. Can I get that? Because then I can, or can you just ship
I'm
the file?
hiding them, Bill.
Why? Why would? I don't care if you got a lock on it. It's fine by me. That's just weird thinking I'm out there, but
Yeah, no, it's not visible unless they send a link. So
okay. Can you shoot me a link on that?
I will on this one. This one doesn't have any of the words, so I was gonna send you this one.
Into the words. There were words in all the other ones?
Mm-hmm.
Great, wonderful. She'll like that. That'll make her happy.
Wait, is she gonna see it?
My supervisor will.
Why?
I was talking about the teacher.
It wasn't your words, it was our
Everybody
words.
else?
Yeah.
What are we talking
Oh, she
about?
don't care about that.
Oh.
It's me that she has nothing to do with that. It's me that she's gonna look at. Because basically what I wanted to do is shoot her one of the longer ones. Because that'll say, okay, well, let's not watch that anymore. You know what I mean? Because she's not gonna want to sit there for 4 hours watching Gen Chem or OChem or
Yeah.
any other kind of chem. You know what I mean?
I have your
My
your text message now, so
Cool.
I'll text you a link to it.
Cool.
Oh,
Okay, just
You get it.
I,
You're an awesome tutor, Bill. We want to love from you.
Hey,
Michigan likes
really?
You have the first link to the first
Honestly.
one, right?
I don't know if I still have. Never get.
You might be able to just forward
well, I
it to
care.
That's the reason why I'm
Actually, I
here.
might have
If
it
not, I
on.
wouldn't be here on a Saturday.
She's like,
Because Saturdays aren't much fun for this.
Actually, I might be able to forward it to you right now, Bill. Because I sent it to Initiative.
Oh, that first one, right?
Yeah, the very first one.
So,
yeah, I have it right here.
you guys remember your this is again a labby thing. Labby. It's labby doodle.
Forward to you again.
It's like, rotation,
You can have. I'm just
measured rotation versus specific rotation, and the enantiomeric excess and that sort of good stuff.
That's a formula.
Mm-hmm. We got one of those on a test. I'm trying to remember if it was a lab final or in class. A couple of us, that equation, in that equation, remember the length is in decimeters. Nobody ever uses decimeters except for that equation. They use decimeters.
Yeah, I know.
Because you're going to measure it in like centimeters or meters, decimeters. You measure it in centimeters, you have to convert it to decimeters. It's 3 times I've said the word decimeter. Okay?
Yeah, that was a lot.
Wrong if you don't. You know what I mean?
That was for last week.
And
But it was it was something over L points times C. Something
It-
like that.
LD. You
Yeah,
look at.
Says this channel does not exist.
Oh, great. Somebody looked at the wording and went, they can't be on here anymore.
And kicked it off.
Have you got the specific for your lab thing for that?
We
Did-
turned that in.
Okay. Anybody got it in their notes? 'Cause I just want to point out, it's a concept, and she did ask it, and since that'll get us there. That'll get us there. Specific rotation, what have you. Cool. Thanks. Okay.
So what's coming ahead for us is stability, acidity and basicity, nucleophiles, electrophiles, and living groups, polar reactions and mechanisms.
Yeah. That's another thing I want to share real quick, so you're not
Preload?
flat-footed on reaction mechanism. I gave you one. That one that we were doing in class the other day for your substitution reaction, SN1 SN2s, that's classic. That's a bromine Levy group. You know what I mean? Classic one. So,
Alpha total, T, is that a T?
yeah. All you're trying to do is compare a specific rotation to a book value. And again, this little L, okay, this is an observed. That's what you're going to get in the experiment. Density, I think is what she's trying to say with D. I call it rho. But again, what's the density of? You're trying to say the density of the molecule you're going through, okay? Because that's what's turning the light, right? So those are the simple little numbers you're going to get. Bit people all over the place.
Got it.
Okay.
Decimeters.
Yes. That's where it is, so you can see it visually. Oh, it's that L that I need to change into decimeters. Okay. What yours was a primary bromine, wasn't it? Chris, the one we were working on the reaction mechanism?
Yeah, I think it was primary bromine.
Primary bromine, and you were replacing it with, what was the chlorine, an HCl or something along those lines?
It was something like that.
What is this regarding?
Okay. This is, I'm going to introduce you guys to
It was
what's
our
called a reaction
pre-lab.
mechanism. Okay? Think,
From last lab, pre-lab, that we turned in.
A reaction profile.
Mm.
SN1, SN2. Those letters stand for nucleophilic substitution. There's two different mechanisms or styles of this. There's a 1 and a 2.
A uni and a biomolecule.
No,
Bimolecular?
nope, it's not about uni or
Uni.
bi or ter. This means that as this leaves, it stops in the middle and becomes a carbocation before you can get what you want to add to
So
it
it
or
has an
substitute for it.
intermediate.
Remember, all this is happening lickety split.
Mm-hmm.
But for a brief moment, it just becomes a carbocation, and which allows the other substitute, in this case, Cl, to come in. It changes stereochemistry. And SN2 will reverse your stereochemistry. In SN1, you get two of them. Because an SN1 can stall. SN2 has to do what's called a backside attack. We'll get there. All I want to show you is what these look like mechanism-wise.
It's gonna be included in the lecture.
Yes. This is where we're going. Okay. But it came up on your lab again.
Yes.
That she wanted the diagram, energy diagram. I was thinking, mechanism. So, what happens with these? This is your leaving group. When you start looking at molecules, you're going to have to start identifying what is your leaving group. In this case, you got a bunch of CHs, right? Those are not leaving groups. Those are really, really bad leaving. You're not going to pull a methyl off or an end of a chain. But this guy,
Is a leading.
because what happens to him if he takes this move?
You can't.
He becomes doesn't he? Is he an electronegative atom? Kind of big. He's not bad. He's not happy. But okay, I'll do it. This is going to be in a solvent of some sort. My choice would be water. So it's going to look like that, okay? And you're going to have to form the other side of the equation. Why did I choose water? Because this will dissociate completely in it. This will now go like, right? It'll dissociate in water like that. But the mechanism okay. What you're doing, does it look somewhat similar to resonance structure arrows? It
Yeah.
should.
I don't understand why that's going to the bromine, whatever, if that's a single, like a pi bond. No, not a
It's
pi
single
bond.
bond, it's an AIM.
It shouldn't move.
It's an
because you
AIM.
have- Okay, you shouldn't move because that's part of your skeleton.
I'm reacting it with this. I'm making a reaction. Okay? You're right. If this was just sitting in water, not a whole hell of a lot happening. Surrounding it. It's in solvent. Because that's what it is. It's in solvent. But I'm reacting it with hydrochloric acid. Okay? What's that doing for me? Bromine is happier with all these than chlorine is by itself. Yeah? Because bromine's bigger, column-wise. If I take this and stick it in water, what happens to hydrochloric acid?
Completely dissociate.
Which means there's a Cl out there with all these electrons, right? Who's happier with all those electrons, bromine or chlorine? So, this leaves, that's my leaving group, while the chlorine simultaneously attacks the carbon. That's got a partial positive, doesn't it? Because ultimately that's what that's going to be in solvent, in water. Do you see what it's doing? Nucleophile, leaving group, mechanism. These electrons are going, nope, I'm going there. I want to be there. This guy's going, all right, I'll trade you. That's an SN2 reaction. Okay. Only difference in SN1, that will be an SN2 reaction because the strength of that nucleophile makes it as an SN2 reaction. And because of polar protic solvent. Now, this will get dicier, but at least you've seen what it is. Why are we looking at all these basicities and positives and negatives and stabilities and what have you? So we can do that and recognize where they are. Where's my leading group? The one that's the most stable. That's the leading group. Where's my nucleophile? The guy that's negative that wants to get to this partial positive charge, which becomes a positive charge as this leaves. Right? If this takes these electrons, this becomes a positive, this becomes a negative. Boom. And you end up with, right? Now, as that happens, if you complete this, this would then, right? That's what's going to happen in the end. So, I won't. I'd give you more of that, but I'll wait so it doesn't get too confusing for you too fast. But that's where we're going. I'm trying to, and that's why we're doing all this, which is why I said lambda max. Okay. Did I use lambda max? Did I look at the sigma? The ACS test? ACS test? You're gonna do this a lot, with some really ugly molecules.
Are you trying to scare us, Bill?
No, I'm just trying to say that if you can, I know you guys are busy and you got stuff you gotta do, I'm probably not the only class you're taking for that matter. If you can kind of get comfortable with, I was trying to give you guys, in fact, I'm gonna pull that out. If I give you guys some solvents, things like that, kind of get used to the names and where they're gonna, what they're gonna do and where are we going. You know what I mean? Try to get a little bit ahead if you can. If you can. Because we're going to do elimination, SN1s, SN2s, eliminations, epoxides, bromonium ions, acid bathe things, hydrogenation, methyl shifts, hydride shifts.
We got it, Bill. We got
You
it.
got it. That's what I like to hear.
We'll be reading this.
Yeah.
We're so excited with those grades. We just want to keep going.
I love this so much. It just doesn't get any better.